Hello, I'm Guillaume Leclerc, and today I'm going to present you cortx-pytorch, which is a library that stores PyTorch datasets in a very efficient manner and allows for fast retrievals and training. Before I dive into the details of the framework, I want to explain how deep learning is usually done. So we take as an input a dataset, which is a collection of small samples, and at each iteration of our training, we collect a random subset of these training points. In most applications, SSDs are used to store each of these files, and therefore collecting them individually doesn't cause any performance issues. However, as deep learning is becoming increasingly popular, companies start buying more and more machines to do deep learning training, which means that they have to buy one SSD per machine and replicate the dataset on each of these machines. This is an incredible waste of resources. Moreover, some datasets are growing so big that they won't even fit on a single machine at all, so this approach doesn't work anymore. To overcome that issue, companies buy dedicated servers that are only going to be used for storage, and other servers, here at the bottom, talk to the storage server to be able to access the data they need for training. To save cost, in most cases, these use spinning disks instead of SSDs too. While this approach is really cost effective, it leads to numerous problems in terms of performance. The first one arises from the fact that spinning disks are used. Since the data we read is random, as displayed by this graph here, we see that the trajectory the head of the spinning disk has to do is much longer than what one would expect, and leads to very poor performance. The second one comes from the fact that we are talking to a machine through the network. Networks can be extremely fast at transporting a lot of data, but there is always an overhead cost as starting a communication. It's like having a big truck. You can transport a lot of things, but it takes a lot of time to just get the driver and leave the town. Since we do a lot of very small requests, one per image in this case, we're basically loading a bunch of trucks with very little data in it, and it creates a lot of overhead. The solution we propose here is twofold. First, the dataset is pre-shuffled before being even uploaded onto Cortex. Then, the files are grouped themselves in bigger shards. This has two advantages. First, because the files were already shuffled, the patterns of access are almost always sequential. As you can see here, the trajectory of the head on the spinning disk is almost always contiguous. Moreover, because files are grouped, now when we query something over the network, a whole shard is transmitted. Therefore, we have a much better utilization of the network. Going back to our previous analogy, the truck is completely full and we have a single transport for a whole batch instead of one per sample. As a result, we obtain a system that can let us utilize our resources at full capacity, whether it is the spinning disks or the network that we have. Moreover, data loading is not a bottleneck anymore, and only the compute is what defines how long it takes to train a model. This approach has been implemented in a package that is available both on GitHub, but also as a pip package directly on PyPy. We will now make a quick demonstration on how to use this package. So the first step is to generate the pre-processed dataset as we explained in the previous slides. Here we just define a client that was going to be used to upload on Cortex, and then we use any PyTorch computer vision dataset, here ImageNet, and we simply pass it to the function upload CV dataset, and it will be converted and directly uploaded on Cortex. As shown here, we simply install the Python package cortx-pytorch, and we run this demo script that we just shown, and the dataset is getting uploaded. We just showed how to process the dataset. Once it's been done once, the only thing we need to do is here instantiate a remote dataset with the same settings that we used to generate it, and then it behaves exactly as a regular PyTorch dataset. You can train and evaluate your models. Same as before, we just run the previously shown script, and the data is directly pulled from Cortex and using no local storage at all. This concludes our presentation. Thank you for watching.